The radioactive element iodine-131 has a half-life of 8 days and is often used to help diagnose patients with thyroid problems. If a certain thyroid procedure requires 0.5 grams and is scheduled to take place in 3 days, what is the minimum amount that must be on hand now, to the nearest hundredth of a gram? So because this is a half-life problem, we know the amount of iodine is decaying exponentially. So this is exponential decay. But what's different about this problem is it's asking us to find what is the minimum amount that must be on hand now, which means we don't know the initial amount. So for continuous exponential growth or exponential decay, we've been using a model that looks like this. A is equal to a sub 0 e to the RT power, which remember is the exact same as the PERT formula that we use with finance when we have interest that is compounded continuously. So they're the same formula, whichever you prefer. A sub 0 is the initial amount, and in PERT, P, which we used for principal, was the initial investment. You could also consider it the initial amount. So either of these models is fine. They're the same model, just a different variable is being used for the initial amount. I'm going to go with PERT. So we want to identify our variables. We already said P was our initial amount, which is unknown. In this case, T, which is time. T is measured in days. And A is the amount of iodine, which is measured in grams. So A will be the number of grams of iodine 131. And I like to organize the information in a table or a T-chart. So it says that the radioactive element iodine-131 has a half-life of 8 days. So it's going to take 8 days for the amount of iodine to decay to half of what we previously had. So right now, at time 0, we don't know the initial amount. So I'm going to leave that generally written as P. It's an unknown amount. But after 8 days, we're going to have half of that unknown amount. So I'm just going to write that generally as 1/2 P. So no matter what P value we had initially, after 8 days, we're going to have half of that P amount. And then we're asked to find, it's told to us that a certain thyroid procedure requires 0.5 grams and is scheduled to take place in 3 days. So in 3 days, we need 0.5 grams. And then we're trying to solve for P. So this is all the information given to us in the problem, organized in a table. So if we take the information regarding the half-life of 8 days, we're going to have half as much as we started with, and we go to our exponential model. Then I'm going to substitute 1/2 P in place of A, and we know that we will have half as much after a time of 8 days. So my substitution looks like that. And you notice we have two unknowns. We don't know P and we don't also know R. We don't know that relative decay rate. But if we divide by P to undo our division, our P's divide out on the right side, but the P's also divide out on the left side, resulting in our equation 1/2 equals E to the R times 8 power. And now this is an exponential equation with only one unknown. So we're going to be able to solve this equation for R. Now remember, this equation is right now in exponential form. So I'm going to rewrite it in logarithmic form. My base right now of this exponential equation is E, so that will become the base of my logarithm. Log base E of 1/2 equals R times 8. Yet we know log base E is really a natural logarithm. So that's natural log of 1/2 equals R times 8. and then we can divide by 8. So natural log of 1/2 equals r times 8. R will equal the natural log of 1/2 divided by 8. And this is going to be a decimal value, so pause and go to your calculator. And you're going to want to store this value in your calculator so that you maintain as much accuracy as possible. And we only round one time in the problem, which would be at the very, very end. So that should be approximately negative 0.0866. That's a rounded decimal. So I'm making note that I'm going to store this value on my graphing calculator. I won't actually use these 4 digits. I'll store it and use the stored value for my future computations. So now if we go back to our exponential model, which was right here, that was our PERT model, we now know the R value. So we'll substitute that into our model. So now we have A is equal to PE to the negative 0.0866 T power. Noting we still don't know the value for P, but we're making progress because we now have found another unknown value. We know R. So now let's go back to our table. So we haven't used this information that in 3 days, when we have this procedure, we need to have 0.5 grams on hand. So we'll substitute in 3 for time and 0.5 for our amount of iodine into our model here. And we should be able to solve for P. So again, the amount we want to have on hand is 0.5 grams. And we want to have that amount in the body after, or I should say in 3 days when we're going to have this procedure. So this is going to allow us to then solve for P. However, note that the exponent here, we know this exponent, it's a number. What we're trying to solve for in this case is P. And P is being multiplied by, there we go, it's going to be multiplied by e raised to this power. So we do not need a logarithm to solve for P here, but rather we're going to just divide by e to the negative 0.0866 times 3 power. And we'll divide by that on both sides. And then we're going to go to our calculator to do this computation. Getting a little messy there, sorry. So remember, when you're going to your calculator to solve for P, we're going to have 0.5 divided by e to the negative 0.0866 times 3 power. However, you're not actually going to type in that decimal. You're going to go ahead and type in whatever stored letter you use. Like on my calculator, I stored this value as x, so I'm going to make sure that I type that in as x times 3. And then that should give us our initial amount. Rounded to 2 decimal places, that looks like 0.65, and that is an amount of iodine which is measured in grams. So it looks like we need to have 0.65 grams given to our patient now in order for us to have in 3 days, have 0.5 grams left in the body.